Okay, we're now in part 3 of the circuit design, and we're going to focus on the output. Now, one of our output components is a fan. Now, a fan basically is just a motor. And this motor, our fan motor, has two terminals. Now, on some of your technical data sheets, you may not see the word pin labeled next to the component, because pins is typically a word used for integrated circuits. If there's not an integrated circuit, for example, these components here are very common for electronics. Microphone, some type of infrared transistor, LEDR, resistor, push button, motor, LED speaker. Normally these components basically have two wires. You can see the wires there. Switch has two wires too. So those are called pins, but they don't call them pin 1, pin 2. Usually it's an input or an output or just two regular connections. Over here it might be a plus and a minus, anode, cathode. But on the microcontroller, as you can see, there are a lot of connections. So they usually call them pins because they look like little pins. And usually in the data sheet they describe what each of these pins represent, because it's not as simple as any of these components. They have multiple connections, and in each one of those connections you must understand the purpose or the function of each connection. So our motor circuit has two connections, probably a plus and a minus. Now if you go back to our original block diagram, we learned that the fan motor cannot be connected directly to the microcontroller because from the data sheet, the microcontroller can only supply 25 milliamps of current. And our fan motor from the data sheet probably needs 100 milliamps of current, which means you need to add an additional circuit that will allow you to operate the fan. A popular circuit to do this is a driver. The general name is driver, but the component name is transistor. And usually that is what is connected to the microcontroller. Notice I'm starting to count backwards. Usually I start from 0 and count up for my inputs, and start from 15 and count backwards for my outputs. Now, a transistor has three parts: collector, emitter, and base. And we learned that the transistor works if you supply a little bit of current in the base, then you will get a lot of current in the collector. And that's just exactly what we need for our motor. Our motor needs a lot of current. Now, where does this current come from? Well, it has to come from a power supply. Well, you could use the same power supply up here, but you have to be sure what is the value of these. I believe for my design, all of these are 5 volts. However, I normally use a 12-volt motor. This is a situation where I need two power supplies. So I'm going to create another power supply called 12 volts and connect my motor to it. So now my 12-volt power supply will provide current for the motor through the transistor and the transistor will be turned on and off by the microcontroller. So this part of the circuit right here is the driver, the C, the B, and the E. You can get a transistor, a single transistor out of the lab to do this, or you can use the Darlington driver integrated circuit and use one of the transistors from that integrated circuit to operate your motor. This could be considered the first draft of a circuit diagram. To save time and to keep things simple, I will stop here. I will not continue with the motion sensor and the lamp. But the idea is to give you some experience with developing a circuit diagram. So let us review and see if I did my job correctly. I have my power rails. For plus. I have my power rails for minus. And I have signal information. Signal information that we say flows through the system. And then sometimes we need extra components or extra wires to complete the job of the system. Here is my completed circuit diagram. Now you would clean this up and make it more professional looking, but at least you have a rough draft as to what the circuit looks like, and also you should indicate what type of signal is at each step. I've indicated here that my temperature sensor outputs an analog voltage that varies according to the temperature at this point. At this point right here, the output will be a series of binary pulses between 0 and 1 at a specific frequency. At this point, my output could either be off or on. Likewise, that will change this, also control this as off or on. And that explains how my signal gets from input and output. Now, when do this come on and off? Well, that is determined by the program that you write for your microcontroller. The important thing to note right now is what are the options. And later we can start talking about the programming part, where we decide to use the program to calculate when I should turn this motor on and off, depending upon a specific value for the temperature. That concludes part 3.